Welcome back. This video is a Forge College production. Last time, we covered best practices in project management with Solana Cloud. Today, we are diving back into our Ethereum fundamentals track with a new topic, scoping and planning the gas analysis report. To understand why planning your analysis matters, I want you to think back to your middle school science fair. There was always that one student whose project was a total disaster. They tried to test everything at once, changing the water, the dirt, the light, and the temperature every single day. Look at this drawing here. With all those variables flashing around, when they were left with a dying plant, they had absolutely no idea which of those changes actually killed it. Then there was the winning project. That student kept the dirt, light, and temperature exactly the same, and only changed one thing, the amount of water. Because they held everything else constant, they proved exactly why their plant thrived. Analyzing the transaction fees, or gas, on Ethereum works the exact same way. If you try to analyze every type of transaction on the network all at once, you are running that chaotic, doomed science project. Gathering a massive, random pile of on-chain data without filtering it creates a mess of noise. You end up with weak conclusions that do not actually tell you how to make your code more efficient. To figure out exactly what drives your transaction costs up or down, you have to treat your analysis like a strict, controlled science experiment. You need to isolate specific causes and effects. Before you write a single line of code to pull data, you need to map out your experiment using 3 structural pillars. First is the independent variable. As we see in this diagram, this is the exact scenario you are testing. Here, we are looking at a simple trade where a user swaps token A for token B. You want to be as specific as possible. Are you looking at a single transfer? A 2-step swap? Or maybe deploying a brand new smart contract? You even want to note the specific contract addresses and versions, as shown in the brackets here. Next, you need your controls. These are the boundaries that filter out the noise and keep your experiment fair. As the diagram expands to show a calendar and a checkmark, we are visually locking our experiment into a specific time window and only looking at successful transactions. Why? Because if you skip filtering out failed transactions or pick a random time frame, sudden network congestion or clumsy user errors will skew your data, making your results completely unreliable. The final pillar is your dependent variables. These are the exact numbers you are going to measure as the output of your experiment. You can see these added to our drawing now as a measuring tape. Instead of guessing, we measure concrete things like the median total gas used, the size of the data sent in the transaction, known as calldata, or the specific cost of the underlying computer instructions, called opcodes. By locking down your independent variable and setting strict controls, you eliminate environmental noise. This guarantees that any changes you see in your measurements are caused entirely by your code and nothing else. Now that the experiment is designed, we need to gather our supplies. Let's translate those metrics into a concrete data checklist, just like the one drawn on this clipboard. We match each metric, like total gas, to exactly where we will find it on the network, like a block receipt. Every piece of data must be mapped to a specific source, either directly on the blockchain or from an external database. You also need to note any quirks, like whether a database might be missing certain hidden internal transactions. This brings us to prioritization. You wouldn't buy a $10,000 electron microscope just to check if your middle school bean sprout needs water. You have to match your tools to the task. Finding out the total gas used for a transaction is like checking the soil with your finger. As you can see, it is cheap, easy to get, and gives you a ton of value immediately. We snap this high-priority block right into place. On the other hand, pulling full opcode traces, which means looking at every single microscopic instruction the computer processed, is incredibly heavy. Look at this tangled web next to our simple block. This is expensive to compute and takes a lot of time. Treat it as a low-priority luxury unless your specific experiment demands it. The smart approach is to start with the cheap, high-value data first. If you absolutely need those deep, expensive diagnostics later, you can take a small, random sample instead of downloading everything. Mapping and prioritizing your checklist protects your time and budget. It lets you answer your biggest questions quickly without getting buried in microscopic details. Before you run a single data query, there is one last step. You must define exactly what a successful optimization looks like. Setting a vague goal like, make the gas lower, is useless. You need a scientifically sound target based on concrete percentiles or medians. A strong success criteria looks like this target right here, aiming for a specific 10% drop in the median total gas used, without accidentally increasing the costs for the heaviest percentiles of users. You also need to set a rule for data quality. Deciding upfront to throw out the results if 70% of your traces are broken ensures your final conclusions will be completely defensible to anyone reviewing your work. A rigorous scope acts as the definitive roadmap, converting a vague optimization dream into a reproducible, actionable dataset for the next phase of the capstone. This video was made by Forge College. Take a moment to finalize your own outlines, because in the next lesson, we are going to use them to actually collect and clean our real-world gas data. To learn more about this subject and explore our other Web3 topics, please visit forge.college.